has two very important features, which are reliability and flow control, as we have mentioned. So for reliability, TCP will provide two things. Will provide reordering of the message and will provide any resistance to packet loss. So not only does TCP provide guarantees on packet loss, but it also reorders the segments in case they arrive unordered on the other TCP node. So remember that the different segments may take different routes on the networks, in which case you may get the segments unordered on the destination. So what TCP does in that case is that TCP will reorder these segments before it sends the segments up to the application layer. So the application layer will get some guarantees from TCP that the segments will arrive in an ordered fashion. So that's the first thing that TCP provides in terms of reliability. The other thing that TCP provides in terms of reliability is the acknowledgement for the segments. So when a segment is sent from one node to another using the TCP connection, the other node has to acknowledge back this segment before the sender will send another segment. So for example, here in this message, the source will send a message that starts from sequence number 1, and this message is 10 bytes. So starting from the sequence number 1 and the message is 10 bytes, so when the other node on the other side receives this segment, the node will send back an acknowledgement with acknowledgement number 11. The acknowledgement number 11 here indicates that I received 10 bytes correctly starting from sequence number 1, and I'm waiting for the next segment, which should start from sequence number 11. So this again indicates that I received all the 10 bytes correctly. Please send me the other segment which starts from sequence number 11, and that's why here the sequence number in the next segment will be 11. If the node on the other side receives this segment, it should send an acknowledgement back with an acknowledgement number which is 21 in that case, because the segment has a length of 10 bytes. So this way TCP provides reliability. If the acknowledgement was not received by this node, then this node realizes that this packet was not received, and in that case it has to resend the packet again. So the way that this works is the fact that when the source sends the segment, it sends the segment with a timer. So this timer will keep running for a particular period of time, and if the node on the other side sends an acknowledgement back before the timer expires, then this is an indication that I received, so I send the next segment and the timer will keep running. If the timer expires before the acknowledgement arrives, then in that case the source will realize that this packet has been lost or this segment has been lost, so it sends the segment again with another timer and so on. So this way the source and the destination will provide reliable communication using TCP. So they use again the response timeout for providing reliability, as we have discussed in chapter 3. So that's how TCP works, and it keeps doing this until the end of the transmission. The other feature of TCP is what we call flow control. For flow control, the TCP tries to avoid the fact that the sender will send too many segments that the receiver will not be able to handle and the network will not be able to handle. So in that case, the way that TCP works is that the receiver will specify what we call a window size. So this window size indicates the number of bytes that the receiver can receive from the sender before the acknowledgement can be sent from the receiver to the sender. Which means that if the window size is 3000, the sender is allowed to send 2 segments, because each segment is 1500 bytes. So in that case, the sender will send only two segments and then wait for the receiver to send an acknowledgement back before the sender can send other segments. So this way, if the window size is 3000, the sender will make sure that it does not send more than 3000 bytes. Otherwise, this will overwhelm the receiver. If the sender receives an acknowledgement back that indicates 3001, and remember here 3001 indicates that I received all the 3000 bytes correctly and I'm waiting for byte number 3001, this indicates that the receiver has cleared the buffer on the other side, and in that case the sender may send more segments to the receiver. The other part of the flow control, which is what we call congestion control. So congestion here tries to avoid the overwhelming of the network. So just like flow control uses the window size, the congestion control here controls this window size. So for example, if I send a segment and this segment is lost, this is an indication that maybe the network is congested and this packet has been lost because the routers are too much jammed. And in that case, sometimes what happens is that the receiver on the other side, and instead of using a window size which is 3000, it actually sends back a window size of 1500 to indicate to sender that I cannot receive more than one segment in that case, and this is to avoid congesting the network. So the way that TCP works is to reduce the window size to avoid congestion on the network. The other protocol in the transport layer, as we said, is UDP, and UDP is the user datagram protocol, and it's very simple protocol. It does not require any overhead for the transport of the segments, and in that case, it's an attractive transport layer protocol which is used by multiple application layer protocols like DNS and DHCP and TFTP and some online gaming, which in this case, these applications, they are loss tolerant and they require some delay requirements which cannot be handled by TCP. So in that case, the main difference between TCP and UDP is that UDP does not provide any flow control, does not provide any congestion control, and it does not even guarantee the ordering of the segments. So here, the segments, if they arrive unordered on the other receiving node, the receiving node will send this to the application as is without having to reorder these datagrams. So there is no guarantee on reliability, and there is no flow control or congestion control done by UDP. To provide these mechanisms that require some kind of overhead, which UDP tries to get rid of this overhead. UDP does not use any connection establishment, but there is a client UDP connection which sends to the server independent datagrams using port number, like as we said, source port number and destination port number, similar to TCP exactly. So again, the different clients will use source port and destination port for the well-known servers like DNS or Radius, and again the clients will use source port number or port numbers in the dynamic range, and they send these individual datagrams to the server, and then the server will respond back with again datagrams by switching the source port and the destination port, similar to what we have talked about for the case of TCP. So the question now is whether we should use TCP or UDP, and as we can see, if the applications require some reliability and you lose segments, this will be a problem for these applications, like for example HTTP or FTP or SMTP or Telnet. These kind of application layer protocols, they require some reliability. If we lose the segments, this will be a problem for these types of applications. And at the same time, these applications are tolerant in terms of delay. In that case, we use TCP. If the applications are tolerant to packet loss, like some video applications, or if these applications they require some delay sensitivity, like for example IPTV or for video streaming and things like that, then UDP is the way to go, or is the proper protocol to choose. So this is the end of this chapter. So to summarize what we have talked about in this chapter, in the first section we talked about the transport layer protocol fundamentals, and we talked about the basic transport layer headers for two cases for TCP and UDP, and then we talked about the different features for UDP and TCP in section 2, and we said that TCP provides some reliability and flow control and congestion control, whereas UDP provides no overhead and no connection establishment, in which case UDP provides more attractive protocol for applications that require less delay and they are more tolerant to packet loss.